Hello friends, so here is another question on thermal expansion of solids. So it is given that a clock with an iron pendulum keeps correct time at 20 degrees Celsius. Calculate the fractional loss in time if the temperature is increased to 40 degrees Celsius. Given the volume expansion coefficient for iron gamma is equal to 36 into 10 to the power minus 6 per degree Celsius. Okay, so basically what the question is, the basic concept is that it's related to a pendulum clock. Okay, so the pendulum clock which oscillates using the principle of simple harmonic motion. If you have studied in waves and oscillations, there is this whole thing which I have discussed in detail. You can check it out. So it starts from the mean position, goes to one extreme, then again goes to the other, and then back to the mean position or the equilibrium position. So the time period of this oscillation, it is given by, for the simple pendulum, it is given by 2 pi root over of L by G. So here acceleration due to gravity and pi, they are all constant, but it is the time period is directly proportional to the square root of the length. So here for for the design of the clock, it is calibrated according to a certain length to give us the correct time. So as the length increases, obviously the time period of oscillation, it will also increase. So here it is given according to the question that this clock is calibrated according to the temperature of 20 degrees Celsius. So why here temperature is there? Because of thermal expansion of solids. Okay, the concept of thermal expansion of solids. Solids expand with temperature, so length increases with temperature. So as length increases, so here there are two things. First is this time period t. So here I will use this subscript time, okay, this for time period, and this is temperature, simply T, that is temperature, and this is the time period of oscillation to differentiate between these two symbols T. Okay, this is for time period of the pendulum, this simple T, capital T, that is for temperature. So as temperature increases, that leads to increase in length, and as length increases, that leads to increase in the time period of the pendulum, time period of oscillation. So the calibration goes awry and it leads to loss in time. Okay, because it takes more time to complete one oscillation. So accordingly the calibration, it goes, there is a mismatch, and and it gives us wrong time, that it leads to loss in time. This is the basic principle. Now let us try to calculate the fractional loss in time. Okay, let's say we take three temperatures. Okay, first 0 degrees Celsius, which is the reference, the base point, 20 degrees Celsius, which is the correct time temperature, and then the increased temperature up to 40 degrees Celsius. Let's say the length of the pendulum at 0 degrees Celsius is L0, the length at 20 degrees Celsius is L20, and the length at 40 degrees Celsius is L40. Okay, it is that much. Now let alpha I be the coefficient of linear expansion of iron. Okay. This. Now we know that as per the concept of linear expansion, increase in length is equal to original length and linear expansion coefficient and rise in temperature. So here L20, the length at 20 degrees Celsius, is equal to the original length or the reference length L0, linear expansion coefficient of iron alpha I, and rise in temperature, that is from 0 to 20 degrees Celsius, delta T is 20. Okay, this much. So this is the rise in temperature, the increase in length, this is delta L20. So L20 is equal to L0 plus alpha I L0 20. Okay, this much. So we can take L0 common, 1 plus 20 alpha I. This. Okay. Then similarly we can write L40 is equal to L0 into 1 plus 40 alpha I. Same thing, same steps, will get the same result. Here the difference in temperature is from 0 to 40, taking 0 degrees Celsius as reference. Same thing, here in place of 20 there will be 40, because from 0 degrees Celsius to 40 degrees Celsius the difference, the rise in temperature, that is 40 degrees Celsius. So that's why this much. So this is L20, this is L40. Now time period of the pendulum at 20 degrees Celsius, that is equal to 2 pi root over of L20 by G, that is equal to 2 pi into root over of this much L0 into 1 plus 20 alpha I by G, this much. This is the time period at 20 degree Celsius. Similarly, the time period at 40 degrees Celsius is equal to 2 pi root over of L40 by G. The length at 40 degrees Celsius, this is here the length at 20 degrees Celsius, is equal to 2 pi root over of L0 into 1 plus 40 alpha I by G. This is the time period of the pendulum at 40 degrees Celsius, which is obviously higher because of the increase in length. Now the pendulum gives correct temperature at 20 degrees Celsius. Here it leads to loss in time because of increase in length, which leads to increase in time period. Now the fractional loss, if we have to calculate, it will be taking the ratio of T40 by T20. Okay, so here T40 by T20, that is equal to 2 pi root over of L0 into 1 plus 40 alpha I by G by 2 pi into root over of L0 into 1 plus 20 alpha I by G. 2 pi, that gets cancelled. Then here it is equal to L0 into 1 plus 40 alpha I by G by L0 into 1 plus okay, L0 into 1 plus 20 alpha I. Okay, this much. So here GG gets cancelled, L0 gets cancelled. So we have 1 plus 40 alpha I by 1 plus 20 alpha I. This is T40 by T20. So we can write it as this whole thing. So we can write this 1 plus 40 alpha I by 1 plus 20 alpha I. We can write it as 1 plus 40 alpha I into 1 by root over of 1 plus 20 alpha I, which is equal to 1 plus 40 alpha I to the power 1 by 2 into 1 plus 20 alpha I to the power minus 1 by 2. We can write it this way, there is no problem. Now we'll be applying binomial theorem. So as per binomial theorem, it becomes 1 plus 40 alpha I by 2, and this becomes 1 minus 20 alpha I by 2. Okay, this much. So this becomes, here it is 20, here it is 10. So now if we simplify it, so now we can write it as 1 plus 20 alpha I into 1 minus 10 alpha I. So it becomes 1 minus 10 alpha I plus 20 alpha I minus 200 alpha I square. Since alpha is very small, alpha I, that the linear expansion coefficient for iron, that is very small, so we can neglect this one, this term, this square term, because it will be very small. So here it becomes 1 plus 10 alpha I. Okay, this much. So the fractional loss in time, so the ratio T40 by T20, this is equal to this much. Now the fractional loss in time is equal to so to calculate the fractional loss in time, we have to understand that the pendulum, it gives us correct time at this much, 20 degree Celsius. As the temperature increases to 40 degrees Celsius, length increases, and as length increases, time period, that also increases, and this leads to loss in time. So this is the correct one. So in order to calculate fractional loss in time, the formula is with respect to T20 at 20 degrees Celsius, that is equal to difference between these two, that is the time period at 40 and the time period at 20 with respect to the time period at 20, because that is the correct time giving temperature, it is calibrated according to that, and that is equal to T40 by T20 minus 1. Okay, this much. So T40 by T20 we have already calculated, that is equal to 1 plus 10 alpha I minus 1, which is equal to 10 alpha I. So here in the question it is given gamma I, that is 36 into 10 to the power minus 6 per degree Celsius. So here we have to use the relationship alpha I is equal to gamma I by 3. So that is equal to 12 into 10 to the power minus 6 degrees Celsius. Okay, so here it becomes 10 into 12 into 10 to the power minus 6. So it is equal to how much? 1.2 into 10 to the power minus 4. Since it is a ratio of same parameters, time periods, so it has no units. So what it basically means is that for every 1 second, for every 1 second of the correct time, for every 1 second of the correct time which the pendulum would have shown if the temperature stayed at 20 degrees Celsius. Okay, this, when the temperature increased to 40 degrees Celsius, it led to a loss of this much time. For every 1 second, loss is 1.2 into 10 to the power minus 47. So in the entire day, for 24 hours, the total loss will be the total loss of time will be for entire day 24 hours, which is 24 hours into 1 hour 60 minutes, 160 seconds, this much. For this much seconds, it will be 1.2 into 10 to the power minus 4 into 24 into 60 into 60. Okay, that is equal to, it is coming around 10.368 seconds. So in the entire day, 24 hours, this much seconds is lost. So the clock is this much seconds behind at 40 degree Celsius. Okay, so this is the thing. Okay, so a very interesting question which kind of bridged waves and oscillations along with thermal expansion, time period of a pendulum and thermal expansion of a material. So a very good question.